So if you take QA, QB and QC as defined in these equations, and you use these ones over here and you calculate the Q net, so you will get 3 by 2 Qm into sine of omega t minus j into cos of omega t. So you will get a rotating vector, because if you look at that one, this is representing a circle. So what will be your result from here? That you will be getting a rotating vector, because as the time will be changing, this theta will be changing, so the radius of this circle will be equal to 3 by 2 into Qm. So your resultant vector will be rotating over this circle. So if you look at this D and Q axis and you take the projection of phase A, B and C and make a vector out of that, so that vector will be rotating over the circle, and the magnitude of that will be equal to 3 by 2 into Qm. Okay, so we get a rotating vector. So now if we change or swap two phases, we will be getting a vector that will be rotating in the opposite direction. So by taking the projection of phase A, B and C over the D and Q axis and combining them for all the time instances, you will be getting a circle. Okay, so the magnitude of the D component will be 3 by 2 times the peak value of your phase A, because if I look at this part, this was your phase A, Q of A, that is equal to Qm into sine of omega t. So this part as a whole is the D component, and this is 3 by 2 into Qm into cos of omega t is your Q component. So your D component is basically equal to your phase A multiplied by 3 by 2. But if I say that I want to keep the magnitude of phase A and the magnitude of phase D equal to each other, so we can write down an expression for the space vector like that. The space vector will be equal to, let's suppose that is equal to Q, that will be equal to 2 by 3 into QA of t plus A into QB of t plus, let's remove this one, plus QC of t into A square. So your space vector is represented by this one, with the condition that the magnitude of phase A and the magnitude of phase D will be same. Basically what we are going to do, I can say that with the help of this transformation, we are transforming this phase A, B, C system into DQ system, means two phase system. So this transformation may be considered as 3 phase to 2 phase transformation. And when you represent your 3 phase system in 2 phase, at any instant of time you will get D and Q component, and you can define a vector using the coordinates D and Q at certain instant of time. At certain other instant of time, this D and Q will be updated, but they will update in such a way that your resultant will be moving over the circle. Basically, if you look at this part, what you have the sine wave from here and you have the cosine wave from here. So basically, if you plot sine and cosine wave with respect to each other, you will get a circle like this. So you get a rotating vector moving over this circle when you transform your 3 phase system into the 2 phase system. So that space vector will be given by this equation. So if you sample phase A, phase B and phase C at any instant of time, you can look at what will be your space vector, means what will be your D and Q component. Okay. So we have seen in the previous lectures that for 180-degree conduction, the phase sequence is like that. We have 8 possible combinations which are shown over here in terms of the switches, switch A, B and C. So for the combination 100, the phase voltages are given like that: 2 by 3 into VDC, minus 1 by 3 into VDC, and VCN is minus 1 by 3 VDC. So now if we use these quantities in the equation that we have just seen above, that your phase space vector Q, that is equal to 2 by 3 into QA plus A times QB plus A square times QC. So now if I take QA in this equal to 2 by 3 from here, and VB is minus 1 by 3, so I can write it like this: minus 1 by 3 into A and then minus 1 by 3 into A square. And we know that A is 2 by taking the value of A, 1 with angle 120 degree, and this is 1 with angle 240 degree. Now if we simplify this one, you will get 2 by 3 with angle 0. So that is the space vector representation for that switching state. Now the switching state 100, for that your phase voltages are given by these values. So now if we use these values in this expression, this one, and we solve it, you will get 2 by 3 with angle 60 degree. Similarly, if you take the next switching state 010, next switching combination, for that phase voltages will be like that, and the resultant space vector can be calculated. That will be equal to 2 by 3 with angle 120. Similarly, for the switching state 100, these are the phase voltages and this is your space vector. For this switching combination, these are the quantities, and so on. You can find out the space vector representation for every switching combination. So there are 8 possible states, and for all of these possible states, you know the phase voltages from the discussion of 180-degree conduction, and you can find out the corresponding space vector representation. Now let's look at that how these states space vectors are represented in the DQ plane. Okay, so if we look at the first switching state, for that the space vector comes out to be 2 by 3 with angle 0, and its coordinate components, D component is this one and the Q component is this one. This is D and this is Q. So D component is 2 by 3, that you can see over here, 2 by 3, and the Q component is 0. So this point is this one, and the magnitude is 2 by 3. So this is our, let's suppose, vector 1. When we are going to apply the switching state 100, this is our switching state 100, that you can see over here, 100, and let's suppose this is the vector 1, and the magnitude of this vector 1 is 2 by 3 and its angle is 0. So that's why it is plotted along the axis. Now if you look at the second switching state 100, let me call this is vector 2, because when it will be represented in space vector, this is 2 by 3 with angle 60. So its magnitude is same, that is 2 by 3, and it is at the angle of 60 degree from your first vector. So this is your V2 when you apply the switching state 110, and its coordinates, D and Q coordinates. So this is D, 1 by 3, and this is Q, 1 by under root 3 that you can see over here. Okay. Similarly, if we sketch the third space vector for this switching combination 0 1 0, so that you can observe over here 0 1 0, that is the switching state. We are going to call it switching vector V3, and its coordinates are minus 1 by 3 and 1 by under root 3. Then similarly for the fourth switching state 0 1 0, our D component is minus 2 by 3 and Q component is 0, and its polar form is 2 by 3 with angle 180. So this is 2 by 3 with angle 180. This is exactly opposite of this one. So vector V1 and V2 are opposite. Okay, now let's look at this switching state. Let me call this is V3, this is V4, so this is V5. So for the switching state V5, we have the combination 001, and the coordinates are these ones, minus 1 by 3 and minus 1 by under root 3. So that you can see over here. And then the next switching state, that is 101, that is over here, and for this the coordinates are 1 by 3 and minus 1 by under root 3. Okay, so we have 6 switching states which are shown over here, these ones. So these are represented in the form of the vectors. So if we combine all of these vectors together, we will get a hexagon. So this is our vector 1, this one is our vector 2, this one is vector 3. So if we combine all of these like this, so you will get a hexagon. Basically, as we have seen in the case of 180-degree conduction inverter, there were 6 intervals like this in the phase voltage waveform. This was equal to 1 by 3 VDC, this was 2 by 3 VDC, this was 1 by 3 VDC, minus 1 by 3 VDC, minus 2 by 3 VDC, and minus 1 by 3 VDC. So when we switch from one state to the other, that is for this interval, let's suppose that this is the representation, then for second interval this is the representation, then for third interval this is the representation, fourth interval this is the representation, fifth and sixth, and after that it will be repeated. So in the D cube plane there will be 6 discrete positions, and you can determine those positions with the help of this equation. Okay. Similarly, if you look at the line voltages for 180-degree conduction inverter for these switching states, 8 switching states 100, 110, 010, 011, 001, 101, and 000 and 111. So our line voltages comes out to be this one. All of these are multiple of VDC or VS, your source voltage. So now if we find out the space vector using the equation as written above, that is equal to 2 by 3 QA plus A into QB plus A square into QC. So you will observe that this comes out to be 2 by under root 3 with angle 30 degree for the first switching state. For second switching state, it is at angle 90, at angle 150, 210, 270, 330. The magnitude remains same. That you can also observe over here in the case of phase space vectors. The magnitude remains same. The angle is going to change. So you have these vectors all of equal magnitude, but they are displaced by the angle of 60 degree with respect to each other. Because you are taking the step of 60 degree over here, 60 degree, then next, then at 60 degree you are changing the state. So at every 60 degree you are changing the state. And we also know that the line voltage waveform for the 180 degree conduction inverter is this one. first switching interval, that is of 60 degree, but with respect to standard cos square waveform, it is 30 degree advance. So that's why you can see the 30 degree over here. Or you can also relate it with the power system, that in the angle between line voltage and phase voltage is equal to 30 degree. Either it is leading or lagging, that depends upon the sequence. So your line voltages will be represented by these space vectors, and for line voltages, if I draw the position in the DQ frame of reference, so let's suppose that this one is D axis, this one is Q axis, and I sketch the first space vector, so that will be somewhere over here at angle 30 degree for the switching state 1 0 0, and let me call it vector 1, but I am going to represent 1L. It means first vector line voltage. Then the second vector will be over here when we will switch from 100 to 110 state. So this is V2L, this is at the angle of 90 degree. So magnitude is same. Then the third position will be this one. This will be at the angle of 150 degree. This is the switching state 010. This switching state was 110. This is vector 3 of the line voltages, and so on. If we sketch them, like this, so you will get a hexagon but rotated by the angle of 30 degree with respect to hexagon of your phase voltages. So if you rotate it by 30 degree, you will get hexagon for the line voltages, and the magnitude of the line voltages V line is under root 3 times V phase, and that you can observe from here. 2 by 3 multiply by under root 3, so this will be equal to 2 by under root 3. So that you can observe over here. The magnitude of the line voltage space vector is under root 3 times the magnitude of your phase voltage space vector. Okay. So now after representing this 180 degree state in the space vector, I am now going to shift to the discussion of generating the voltage with the help of certain number of supplies. Let's suppose that we have the load and I have 3 supplies, one of 10 volt, the other one is of 5 volt and the other one is of 0 volt, and all of them are connected to the load through the switch S1, S2 and S3. When I will be turning on the switch S1, the load voltage will be equal to 10 volt. If I turn on switch S2 and turn off the all other switches, S1 is turned off, so I am just going to de-highlight this one. S2 is on, so our load voltage will be 5 volt. Now if I turn on switch S3, our load voltage will be 0. So I can get either 5 volt over here, or I can get 10 volt over here, or the 0 volt across the load. I cannot get any other voltage. But if I say that I want to have 7.5 volt across the load, what I will have to do? First of all, I will have to use the switching. Let's suppose that we decide that our switching frequency is this one. In this interval, I switch on S1. So when I will switch on S1, our load voltage will be 10 volt. Then I turn off S1 and turn on S2, so our load voltage will be equal to 5 volt. And then I turn off S2 and turn on S3, our load voltage will be 0 volt. And then I repeat the process, or I use some other combination. Let's suppose that in this interval we have turned on S2, we get 5 volt. Then we turn on S1, we get 10 volt. Then we turn on S3, we will get 0 volt. But we are going to turn them for such interval of time that average voltage that we get is 7.5 volt in that switching interval. So how you calculate the average voltage? That is calculated by having the information of the duty cycle. That if you have this waveform like this, if I ask you that calculate the average voltage of this waveform, average voltage will be somewhere over here. So how you will calculate? Let's suppose this is plus Vs and this is the 0 volt and the switching interval is Ts. So V average will be equal to duty cycle times the Vs. And what is the duty cycle? Duty cycle is basically the on time compared with the complete time. Let's suppose that this time is T on, for which your switch was turned on, and then it is off. So T on divided by Ts is the duty cycle. So V average is equal to T on by Ts into Vs. So if you know the on time out of the total time, you can find out what will be the average voltage because of that supply. Okay. So now the average voltage because of 10 volt in this interval can be calculated as V average, that is equal to, let's suppose the on time is T1 and the total time is Ts, into Vs, and Vs is 10 volt, the average voltage because of the 10 volt source. Now if I want to calculate the average voltage because of the 5 volt source in this interval, so that will be equal to V average 5 volt T2 divided by Ts into Vs, and for this Vs will be 5 volt. And then the average voltage because of 0 volt supply, definitely it is going to be 0 because Vs is 0, but we can write it like that, T3 by Ts into Vs. So we can find out the duty cycle for each source. For first source the duty cycle is this one, for the second source the duty cycle is this one, for third source duty cycle is this one. So we will get V01 because of the switching on the first source of 10 volt, then V02 is the average voltage because of the second source, and then V03 is the average voltage because of third source. So if we sum them together, we will get the net output voltage in one switching interval. Okay. Similarly, if I say that I have these vectors, the switching states over here, for phase voltages we have these switching states, this 1 0 0, let's suppose that this is one source. If we apply the switching state 1 0 0 in the inverter, we will get this output voltage, and if we apply the switching state 1 0 0 in the inverter, we will get this voltage at the output 2 by 3 in that position of 60 degree. So now if I say that I have these vectors as the sources, let's suppose this is vector 1 2 by 3 with angle 0, this is vector 2 2 by 3 with angle 60, and this is vector 0 or vector 7, those are the null vectors, 0 with angle 0. So this S1 is basically representing the switching combination 1 0 0. If we apply 1 0 0, it means across the load we will be getting V1, the voltage over here will be V1. And let's suppose that we are going to turn on this switch for the time t1, so vector V1 will be available for the time t1 at the output. Now if we apply the second switching state 100, so our this second source V2 will be connected and our load voltage will be equal to V2 for the time T2. And then if I turn on the switch 3, our load voltage will be equal to either V0 or V7, whatever is our source, for the time, let us suppose T0 or T3. So V0 or V7 will be there, one of them will be used. So definitely, as our V0 or V7 gives us the 0 volt, these are the null vectors, so our output voltage will be 0. So we can calculate the duty cycle for each source D1, D2 and D3 with the help of these expressions. And let's suppose this is arbitrary. We suppose D1 is equal to 0.5, D2 is 0.3 and D3 is 0.2, because sum of all of these, the duty cycle of this part D1, the duty cycle of this source D2 and duty cycle of this one D3, sum of all these must be equal to 1. So D1 is 0.5, 0.3 and 0.2, let's suppose, and now if we calculate the resultant will be this one. Right? Okay. So what we have learned from here, that if we want to construct certain voltage, we want to develop certain voltage across the load, what we will have to do, we will have to decide about the duty cycle of these switches, the operational duty cycle, for how much time they must be turned on in one switching interval. Then you can find out what will be your output DC voltage, your output voltage. Okay. So you need to look at the duty cycles. Duty cycle of these switches, and once it is calculated, now you can apply these switching states to get any desired output voltage. Let's suppose I want to construct a voltage with magnitude V reference and whose angle is alpha, and I have these three switching states V1, V2 and V0 or V7. So I will apply this state for D1, I will apply this one for D2 and I will apply this one for D3. So our output voltage, that is V0, that will be equal to V reference into alpha. For this I can calculate what should be D1, what should be D2, what should be D3. And if I calculate that one and I switch this vector V1, V2 and V0 by V7 for that time, because this is the fraction of the time T3 over Ts, this is T2 over Ts, this one is T1 over Ts. These are the fraction of times. So if I switch for these fraction of times, what I will get? I will get V reference at the output.